In this sixth module, we're discussing electric interactions and the Higgs mechanism. In this 12th video, we will encounter the particle associated with the Higgs field, the Higgs boson. After following this video, you should know how the Higgs boson is produced at the LHC, how we identify its production and decay, and how it is verified that it has the properties required for a Higgs boson. The Higgs field is a microscopic field that must be quantized. There is a particle which corresponds to the phi field, the scalar Higgs boson H0. All its properties were known before it was discovered, except that we didn't know whether it existed and that we didn't know its mass. In particular, its branching ratio into different fermion-antifermion or boson-boson pairs are fixed once the mass is known. The Higgs boson can be produced as a real particle at a hadron collider, provided its energy is sufficient. This is for the first time the case at the LHC. Here we show some Feynman diagrams for the production of a Higgs boson from two protons, either by quarks or by gluons in the initial state. The existence of the Higgs boson H0 has been confirmed in a spectacular way by the experiments ATLAS and CMS at the LHC in 2012. Higgs boson production is detected, among other methods, in the invariant mass distribution of photon pairs or pairs of Z bosons. The latter ones decay in turn into lepton-antilepton pairs, which are then observed in the detector. A 4-lepton event from the ATLAS experiment with 4 muons in the final state serves as the logo of this course, so we've seen it many times. The signal at a mass of about 125 GeV sticks out clearly above the background of other production mechanisms which do not involve Higgs bosons. On the left you see the invariant mass distributions of 2 photons, which has a peak at 125 GeV, and on the right you see the invariant mass of the 4-lepton system that comes from a Higgs decay into ZZ pairs. Indeed, we have here a second nice example of particle mass measurement through the invariant mass of its decay products. The measurements from the two experiments at the LHC give compatible results which can be combined. This determines today the mass of the Higgs boson H0 to be 125 GeV with a precision of about 250 MeV, that is accurate to about 2 parts per thousand. This is a remarkable achievement by these experiments and is the fruit of the work of thousands of physicists and engineers during 2 decades. The experimental findings today can be summarized as follows. The H0 is clearly a well-established new particle. The probability that background fluctuates upwards to simulate the signal is of the order of 1 to several hundred million. It is indeed a boson because it decays into 2 photons. It very probably has spin 0. Its couplings to different particles are indeed proportional to their apparent masses, as they should. Here we show a summary of results from the CMS experiment. The only particle or coupling that is missing here is the Higgs coupling to itself, since the Higgs boson should also be responsible for generating its own mass. So that will come in the future. But we are thus sure already at this point that H0 is indeed a Higgs boson. This, however, does not exclude the existence of other bosons of this type, which are obviously actively hunted by experiments at the LHC. In the next module, Anna will go into more details about how to search for new phenomena in the challenging environment of a hadron collider. If you want to know more about the Higgs mechanism and its working principles, I recommend these 3 episodes of the excellent series Minute Physics from the Perimeter Institute in Waterloo, Canada. You will easily find them on YouTube. To conclude our discussion of the Higgs boson, the next video contains an interview with one of the key people who contributed to its discovery.